exploring how surfactant gradients create self-amplifying flows and bistable behaviors in microfluidic systems. A tiny drop of soap on calm water races outward in all directions due to surface tension gradients. Let's understand how surfactant gradients self-amplify when flow slows down. Surfactants create concentration gradients along the interface, which drive powerful flows through surface tension variations. Surface tension gradients arise from concentration gradients of the surfactant. When flow is fast, convection washes away the concentration gradients, weakening the effect. But at lower speeds, concentration gradients can build up, creating stronger self-propulsion as you reduce pressure. Here we see a concentration gradient from high to low surfactant concentration, driving flow downward through Marangoni stress. Let's calculate the actual stress generated by a small concentration contrast. The surface tension sensitivity to concentration is about 10 to the minus 2 newtons per meter per millimolar. Consider a concentration difference of 0.1 millimolar sustained over half a millimeter. This gives a concentration gradient of 200 millimolar per meter. The resulting Marangoni stress is about 2 pascals, which is surprisingly large at the microscale. A few pascals at microscale is significant, easily comparable to typical viscous pressure drops in microchannels. Now let's explore the N-shaped pressure flow relationship that creates bistability. The N-shaped curve shows pressure versus flow rate. Notice the middle section with negative slope, where flow increases as pressure decreases. Turning down the pressure knob produces counterintuitive behavior. Flow drops normally, then rises in the negative slope region, then drops again. This backbending creates two stable operating points with a jump between them, giving the system memory or hysteresis. Add a bit of compliance like bubbles or soft walls, and you get self-oscillations useful for timing and pumping without any valves. Let's write down a simple law that captures this backbending behavior. Pressure equals viscous resistance times velocity minus a Marangoni assist term that decreases as velocity increases. Taking the derivative gives the slope, which is viscous resistance, minus a negative term that can dominate. Using realistic numbers, viscous resistance 10 to the 4 Pascal seconds per meter, Marangoni assist 1.5 times 10 to the 4 pascals. Critical velocity is 5 millimeters per second. At the critical velocity, the negative term is about 7.5 times 10 to the 5 Pascal seconds per meter, much larger than the viscous resistance. This confirms a negative slope region exists, where the Marangoni assist dominates viscous resistance. Now let's design a practical valveless pump using these principles. A shallow film under a steady temperature or surfactant gradient slides along without any external pressure source. The interfacial shear from the gradient translates directly to a mean velocity in the film. Velocity is roughly Marangoni stress times film thickness divided by viscosity. Thinner films amplify the effect, giving large shear rates from tiny surface stresses, perfect for low-power microfluidic pumps. Let's calculate the achievable pumping speed with realistic numbers. Marangoni stress equals surface tension difference divided by length scale. Take a surface tension difference of 1 millinewton per meter over 1 millimeter. This gives a Marangoni stress of 1 pascal, with film thickness 50 micrometers and viscosity 1 millipascal second. Velocity is about 0.05 meters per second, or 5 centimeters per second, from a tiny surface tension contrast. That's an impressive 5 centimeters per second pumping speed from a minimal surface tension difference. How do we measure this phenomenon without getting fooled by artifacts? The key is to sweep pressure up and down while maintaining a fixed thermal or surfactant gradient. Plot flow rate Q versus pressure difference to reveal the characteristic curve. The curve loop showing hysteresis, with different paths for pressure increasing versus decreasing. The hysteresis loop confirms this is real physics, not just sensor drift or experimental artifacts. Using fast pressure control and small volume compliance lets you trace the unstable segment indirectly through oscillation onset. What are the target numbers we should aim for in experiments? From earlier, viscous resistance coefficient is 1.6 times 10 to the 4 Pascal seconds per meter. at velocities from 3 to 6 millimeters per second. Viscous pressure drop is 48 to 96 pascals across this range. If Marangoni assist increases from 120 to 180 pascals as velocity drops, net required pressure decreases with increasing velocity, giving clear negative differential resistance you can measure. Finally, let's understand when this phenomenon works and when it fails. Too much driving pressure scrubs gradients clean, returning to normal positive resistance behavior. Too little drive in diffusion smooths out the gradients before they can build up. The design space has a sweet spot where gradients persist and the interface stays stable, with failure modes on either side. 3 key dimensionless numbers guide the design: Marangoni number, Peclet number, and capillary number. Peclet number equals velocity times length divided by diffusivity, measuring convection versus diffusion. Capillary number equals viscosity times velocity divided by surface tension, measuring interface shape stability. Let's calculate the dimensionless numbers for a typical sweet spot design. With velocity 0.05 meters per second, viscosity 10 to the minus 3, and surface tension 0.07, capillary number is about 7 times 10 to the minus 4, keeping the meniscus stable. With length scale 1 millimeter and diffusivity 10 to the minus 9 square meters per second. Peclet number is about 5 times 10 to the 4, meaning convection dominates and gradients can persist. Marangoni number is in the thousands to 10,000s range, indicating strong surface drive. This triangle of large Marangoni number, large Peclet number, and small capillary number defines where negative capillary resistance appears most readily. Operating in this regime enables practical valveless microfluidic pumps that exploit surface tension gradients for propulsion,